Ever wonder what makes a diamond the hardest thing on Earth, or why a copper wire conducts electricity so well? Well, the answers aren't what you see on the outside. They're hidden deep inside in the secret architecture of solids. So let's dive into this hidden world, because it's this internal structure that defines pretty much everything about the solid world around us.
So think about this for a second. Why is it that when you smash a salt crystal, it breaks into these tiny, perfect little cubes, but when you shatter glass, it just explodes into a chaotic mess of random, sharp pieces? I mean, they're both solids, right? So what gives?
Well, the answer to our little mystery lies deep inside, in how their atoms are arranged. And this one difference creates a huge divide, splitting almost all solids into two basic categories, one of perfect, repeating order, and one of total, frozen chaos.
And here's that great divide laid out for us. On one side, you have crystalline solids. This is where atoms are locked into a perfect, repeating 3D pattern we call a crystal lattice. This incredible internal order is why they have a sharp, specific melting point, like salt, ice, or a diamond. But then, on the other side, you've got amorphous solids. Their atoms are just a random, jumbled-up mess, and that's why they don't really melt, they just get softer and softer over a range of temperatures. Glass, rubber, plastic, those are your classic examples here.
You know, the word amorphous literally means shapeless. And a great way to think about these solids is to picture them as supercooled liquids. Their atoms were basically frozen in place so fast that they never got the chance to line up properly. So they're just stuck in this permanent state of atomic chaos. Okay, so let's leave that chaos behind for a minute and jump back into the world of order. Because even in the predictable world of crystalline solids, there's a ton of variety. And it all comes down to the type of atomic glue that holds them together. This sorts them neatly into 4 distinct families.
First up, we've got ionic solids. In these, positive and negative ions are locked together by these really powerful electrostatic forces. It's like they're held together by billions of tiny, super strong magnets. That attraction is what makes them incredibly hard and gives them such high melting points. But that rigid structure, it's also their biggest weakness. If you nudge the layers just a tiny bit, all of a sudden, positive repels positive, and the whole thing just shatters. And yep, that's your table salt. Next up are covalent solids. Here, the atoms don't just attract each other. They actually share electrons, creating this unbreakable, interconnected web. Now, what this means is that a covalent crystal isn't made of a bunch of individual molecules. The entire crystal is basically one giant supermolecule. That's why diamond, which is just pure carbon, is one of the hardest materials we know of.
Then we have molecular solids. Now, unlike that supermolecule of a diamond, these are made of separate, individual molecules, like H2O molecules in ice. And the forces holding these molecules together are much, much weaker, because that atomic glue is so flimsy, it doesn't take much energy at all to pull them apart. And that's exactly why they're usually soft and have really low melting points.
And finally, our 4th family, metallic solids. And these have a really unique structure. I want you to picture an orderly grid of positive metal ions, but their outer electrons have kind of broken free, and now they're forming this flowing sea of electrons that just surrounds everything. It's this moving sea of charge that makes metals such amazing conductors of heat and electricity. And it lets the ions slide past each other, which is why you can bend a metal instead of it just shattering.
So just a quick recap here. You've got ionic bonds, which give you hard but brittle solids. You have covalent networks, which create extreme hardness. Then there are those weak intermolecular forces, which result in soft, low melting point solids. And finally, that metallic sea of electrons gives us conductivity and malleability. 4 different kinds of glue, 4 totally different results. Okay, so we know there are these different crystal families. But how does nature actually build these incredibly precise ordered structures from the atom up? Well, it turns out it all starts with a simple blueprint. See, building a crystal is basically a 3-step process. First, you start with lattice points. That's just a fancy way of saying the specific locations where the atoms are. Then you define the smallest possible repeating block of these atoms. This is the really crucial part, and it's called the unit cell. You can think of it like the fundamental Lego brick of the crystal. And finally, you just repeat that one unit cell over and over and over again in 3 dimensions to build the entire structure, the crystal lattice.
And here's the amazing part. Depending on the exact shape of that unit cell, the length of its sides, the angles of its corners, you get different master blueprints. In fact, every single crystal in the universe conforms to one of just 7 of these fundamental systems. They range from the perfect symmetry of the cubic system, which gives us our salt cubes,
all the way to the much more irregular triclinic system. It's like nature's own architectural guidebook.
And to really appreciate what that symmetry means, let's go back to that simple cubic crystal, like salt. If you were to analyze it, you'd find 23 distinct elements of symmetry. 23! That means there are 23 different ways you can rotate it, flip it, or reflect it, and it'll look completely unchanged. It's mathematical perfection made real.
But here is where our story takes a really fascinating twist. For all this talk about perfection and order, it turns out that perfect crystals are basically a myth. And in the real world, it's often their flaws that make them so interesting and useful.
Yeah, this is a fundamental truth of materials science. Every single crystal that exists in the real world has defects. Now, these aren't necessarily bad things. In fact, a lot of the time, these imperfections are what give materials their most unique and valuable properties. So what do these defects even look like? Well, one common type is called a Schottky defect, and it's pretty straightforward. It's just a vacancy. Imagine a perfectly built brick wall, but one brick is just missing. In an ionic crystal, a pair of oppositely charged ions disappears, which keeps the whole crystal electrically neutral but leaves behind a tiny atom-sized hole.
Then you've got the Frankel defect. In this case, no one's missing from the party. Instead, an ion gets knocked out of its proper spot in the lattice and crams itself into a tiny space between other atoms where it just doesn't belong. It's like a guest leaving their assigned room to go sleep in the hallway instead.
And this brings us to a really cool final thought. We've seen that the secret architecture inside solids is what dictates all their properties. But we've also seen that perfect order isn't the whole story. These so-called defects can stop a crack from spreading. They can allow charges to flow. They can even change a material's color. So if a perfect crystal is often brittle, but an imperfect one can be strong and useful, it really makes you wonder, what other secrets are hiding in the flaws?